Alright, so today we'll complete the rest of the topics that we started uh, about recursion. So we discussed until output statements for debugging, and we'll continue with creating a recursive method. So basically we are pulling everything together, and we'll talk about how to create your own recursive method from scratch. So at this point, you have seen recursion in action, factorials, searches, traces, but when you're the when you're the one designing it, the process can feel a little mysterious. So I want to give you a simple checklist that you can reuse every time you write one. First is you define the problem clearly. So start by describing in plain English what your method is supposed to do. For example, reverse a string or sum all elements in a list. So you should be able to explain the task without even thinking about recursion yet. That's the first step. Second step is identifying the base case. So every recursive method needs a base case, the point where the method stops calling itself. So this is usually the simplest version of the problem that you can answer immediately. So for reversing a string, the base case could be if the string's length is 0 or 1, just return the string itself. That's your stop sign. No more recursion past that point. So that's the second step. Third step is define the smaller subproblem. So how can I make the problem smaller? For string reversal, the small version is reverse everything except the first character. So in code, that's like taking the substring from index 1 onward, and that's your tail, and calling your own method on that. Then when smaller string is reverse, you simply track the first character on the at the end. So if your string is cat, the reverse would be uh, so if you take cat, the reverse is basically you'll take 80 and then it's gonna be ta. So then you combine uh, ta with c. So that's so each recursive call just peels off one character until the base case is reached, and then you combine the results. The next step is combining the results. So this is where recursive really shines. You take the results of those small problems and combine them into a full answer. The combining step depends on what you're doing. For summing, you add results together. For searching, you check and return found values. For reversal, you append characters together. So it's base case. First is base case, smaller problem, and combine. That's the core idea of every recursive function. And then you validate inputs early. So before going into recursion, make sure your inputs make sense. If you get a null string or a negative number, handle that before calling yourself recursively. That prevents crashes and infinite recursion later on. And few things to avoid, watch out for, is forgetting multiple base cases. So sometimes you need more than one, like both an empty string and a single character string. And other thing is string concatenation in deep recursion can get expensive because strings are immutable. You can mention or explore using string builder in advanced cases, but for now clarity is more important than micro optimization. So the key is to keep your logic correct and readable first, and efficiency can come later. So that's about creating a recursive method. Next we have recursive math methods. So let's look at one of the most common areas where recursion shows up, which is math problems. You've probably seen examples like factorial or Fibonacci series. uh, numbers before, but now we are going into a bit deeper into how they really work and why some versions are much better than others. So let's take the classic example, which is factorial. The factorial of a number is the perfect example of a clean recursive definition. So when we say uh, n factorial, uh, which is equals to n multiplied by n minus 1, this is your factorial, and when n equals 1, we stop because 1 factorial is 1. So when you call factorial 4, it goes 4 multiplied by uh, factorial of yeah. So n is equal to 4. Uh, so that will be n 4 multiplied by 4 minus 1, 3, which is factorial 3. So that gives us uh, 4 multiplied by 3 factorial, and this gives us again 3 multiplied by 2 factorial. It goes on, then returns 1, builds all the way back up. Each recursive call handles one smaller piece of the problem. Multiply, step down, repeat. So that's a simple case, and recursion fits beautifully because math definition itself is recursive. So then we go to Fibonacci series. Fibonacci numbers are great example, and has a great warning sign. So the Fibonacci uh, sequence starts something like this: 2, 3, 5, 5, 8. Each number is the sum of the two before it. So the formula would be uh, n minus 1 uh, plus Fibonacci n minus 2 uh, with the base cases and so these are the base cases. So at first that looks like a perfect recursive definition, but there's a problem. If you write it directly that way, each call to Fibonacci n ends up recomputing the same numbers over and over again. For example, Fibonacci 5 calls Fibonacci 4 and Fibonacci 3, then Fibonacci 4 calls 3 and 2. So the Fibonacci 3 gets computed twice, and that happens exponentially as n grows. So this naive version of Fibonacci looks nice but runs really slow for even moderately large n, say 50 or 40. That's millions of unnecessary calls. How do you fix it uh, is using memoization, which it's a smart we make it smart with memoization, which is that just means caching results you have already computed. We can use a map or even a simple array to store results for each n after we compute it once, and then before doing any recursion we check the map first. If the value is there, we just return it, and the one small change makes the algorithm run in linear time instead of exponential. So Fibonacci 50 goes over several million calls to just 50. So that's a big difference. You can think of memoization as giving recursion a little bit of memory so it doesn't keep forgetting what it already learned. uh, so recursive math methods are great for showing how recursion works, but they also show why you have to be mindful of efficiency. So sometimes recursion makes things cleaner and more readable, but if you're repeating the small calls, you might need to cache or forget it into convert into iterative or bottom up version. You don't need to master dynamic programming yet, but just understand that recursion can be powerful but wasteful if used blindly. Next, we have let's talk about one of the most interesting uses of recursion, exploring all possibilities, which is also called as backtracking. This is a kind of recursion that powers things like generating all subsets of a list, finding all possible paths in a maze, or solving puzzles like Sudoku and N Queen's problem. The main idea is that your method explores one possible math, and when it's done with that, it backs up or backtracks and tries a different one. So the backtracking pattern, you can think of it like a repeating cycle. First comes choose, you explore, and then you unchoose. Choose is basically you make a decision, pick an element, add something to your path, place a piece on a board. Explore, call the method recursively to explore what happens with that choice. Unchoose is undo the change so you can try something else next time. This unchoose step is what makes backtracking special. It allows one recursive call to clean up before exploring the next branch. An example is, let's take a simple example. Um, you can imagine right in your head generating all subsets of a small list like 1 2 3. Yeah, this is we are generating all subsets of this small list. So here's how recursive logic goes. At each step you have a choice: either include the current element or skip it. You move through the list one element at a time, and at the end you print or collect the subset you've built so far. So for 1 2 3, the result would be like first it would be empty, then we would see 3, and then 2 2 comma 3, 1 1 comma 3, uh, then 1 comma 2, uh, then altogether 1 comma 2 comma 3. So the recursive handles all the branching for you. You just need to tell how to choose, explore and unchoose. So and we have state management. So when you're doing this, you often work with mutable structure, maybe like a string list integer or a board that represents your current state. So each recursive call modifies that state, like adding a number to the current subset. But it's really important that you undo the change afterward. That's the unchoose step. So if you forget to do that, one branch's changes can leak into the next branch, and your results will be wrong. So think of it like exploring a maze. You move forward, mark your path, and when you hit a dead end, you back up and unmark that path, trying a new direction. And few things to avoid is, there are some couple of classic mistakes in backtracking. The first is forgetting to unchoose, which corrupts your state because the next branch starts in the wrong condition. The second is letting global or shared state leak between branches. Each recursive call should get a clean, accurate view of current partial solution. If your output looks duplicate, missing, or oddly combined, that's usually the culprit. Why it matters is because backtracking shows up all over computer science. It's the foundation of algorithms that needs to try everything, but in a structured way. And what's cool is that this is the same pattern: choose, explore, unchoose applies whether you are generating subsets, permutations, paths in a grid, or even making decisions in a game tree. uh, yeah, that's about backtracking. Next we have Stack Overflow. Let's talk about something every programmer hits at least once, which is Stack Overflow. uh, it's not a website. The actual runtime error that happens when recursive goes too deep. Uh, so what really happens is, every time your program calls a method, Java creates a stack frame, a little memory box that stores the that method's parameters, local variables, and return address. So when one method calls another, a new box is added on the top of the stack. When the method finishes, the box is popped off. But if you keep calling methods and never finish them, the stack keeps growing and eventually it runs out of memory. That's what triggers a Stack Overflow error. So why it happens? The most common reason is missing or incorrect base cases in recursion. For example, if you write a method like countdown int n and forget to stop when n hits 0, it just keeps calling itself with smaller and smaller numbers until Java can't handle it anymore. Even worse, if the input is too big, say you call countdown integer dot max value, you'll also hit a Stack Overflow because the call depth is uh, enormous. So even if your base case is correct, recursion can still fail when the problem grows beyond what the call stack can hold. How to fix or avoid it? There are few ways to deal with this. You convert to an iterative approach when recursion isn't essential. Loops don't add to call stack the same way. You add memoization. If your recursion repeats work, that reduces the number of calls dramatically. And limit the input. So for example, don't let the user enter absurdly large number. If you know recursion depth will explode. So, and just to clarify, Java doesn't do tail call optimization unlike some other languages. That means even if your recursive call is the last line in the method, Java still keeps that stack frame. It doesn't reuse it. Uh, like for example, if you wrote something like count down uh, integer uh, integer dot max uh, value, you'd quickly blow the stack because that's over 2 billion recursive calls. So but if you replace that recursion with a simple loop like a for or a while that decrements, it runs instantly and uses almost no memory. So there are a few main things to watch out for: is forgetting a proper base case or making one that never triggers. And assuming Java optimizes recursion away, it doesn't. And ignoring input constraints and letting recursion go unchecked. Uh, Last topic is an example, which is recursively output permutations. So let's wrap up this topic with an example which is generating all permutations recursively. So this is one of the cleanest examples on of how recursion and backtracking work together to explore every possible arrangement of items. The concept is here is a permutation is simply every possible ordering of a set of elements. So if you have characters ABC, the permutations will be like ABC, ACB, BAC, all the possible set of elements, uh, all the possible set of combinations. So to get all of them, we use recursion to fix one element at a time and swap it with others to explore all possibilities. So this pattern is pure backtracking. We make a choice, we explore deeper, and then undo that choice before trying a next one. So how it works is, here's the idea. We write a method like permute, uh, we character, let's say, uh, and then we have an index. So at each recursive call, the index marks the position we are currently fixing. So if index reaches the end of the array, which is index, uh, we check it with the length. Uh, so we have built one complete permutation, so we print it. So otherwise we loop through every element from the index to the end. You swap the current element with the element at the index and recurse with index plus 1 to handle the next position, and then swap them back. That's how unchoose step, that's the unchoose step. So the array goes back to its original form for the next loop. So that recurse swap back pattern is the backbone of this algorithm. uh, Now let's say we have so we have ABC. So you start at index 0, which is you swap A, recurse, and at index 1 you have B, recurse. At index 2 you print ABC, uh, and then you swap B and C, recurse again, print ACB, backtrack, swap A and B, recurse, generate all permutations starting with B, and so on until all possibilities are printed. So you'll notice each branch builds a new order and then resets before the next. That's classic backtracking. And the performance is for this permutations grow very fast. So the total number is n multiplied by n factorial. So even for 5 elements, that's 5 multiplied by 120, which is 600 calls. So always keep n small in demos or tests, maybe 4 or fewer, or you'll flood your console. So if your input has duplicates, you'll get repeated results unless you handle that with boolean uh, visited array or skip logic for repeated elements. Uh, so few common mistakes to avoid here is forgetting to swap back after recursion. So your data will stay scrambled for the next branch. Printing too many results, you limit or filter output to keep it readable, and ignoring duplicates in the input, you'll see repeated permutations. So that's about this topic.